Hello, today I'm going to be talking about the normal probability distribution. Generally in statistics, there are different types of probability distribution, but broadly speaking, they are categorized into two, the discrete probability distribution and the continuous probability distribution. Now, of the continuous probability distribution, the normal probability distribution is a unique and a central example in statistics. In fact, the normal probability distribution is central to statistics generally. And we're going to be looking at it in detail, what it is and how it is actually applied in biological science. So the learning focus, we're going to look at the normal distribution itself. We attempt to look at how it was established, how it was created, and what it actually applies to. And then we're going to see how we can determine normal probabilities, and then find the value that corresponds to normal probability. And then in subsequent video, we'll be looking at how we can assess departure from normality. Now, normal distribution is otherwise described as a probability density function curve. It is a curve. Usually, it forms a dumbbell-shaped curve. But in essence, what are we talking about? Usually, biological data, when taken from a population and plotted on a graph, will usually give us a dumbbell shape. Okay? So when we say a data set is normally distributed, we are simply saying it follows the expected curve, the expected pattern. In other words, we can say this is typical of a biological distribution. And this has been observed in biological distributions in different fields. It was first described by De Nouveau in 1733, and it was further elaborated on in 1812 by Laplace. And essentially, like I mentioned, it describes some natural phenomena. If you took the age of students within a particular class and you plot it on a graph, it's likely going to form a curve of normal distribution. If you took whatever biological parameter, maybe talk about height, weight of a cohort, a set of people, a unique group of people, maybe a particular cadre, you're going to see it forming that particular curve if you plotted it on a graph, like a kind of histogram. So more importantly, it describes sampling characteristics of our total population, and it also look at the mean of that particular population. So again, we call it the normal probability density curve. The curve we obtain by the time we plot that particular graph, when we enter our data on the graph, we're going to end up with that particular curve called the normal probability density curve. In short, we call it the PDF curve. Okay. Usually, the data we plot on it are described as continuous random variables. Usually, they are continuous in nature. There are two types of variables. You can have a discrete variable. These are variables that usually take a simple whole number, while the continuous random variables, they take value between two whole numbers. So you can have decimal fraction in continuous variable. So, and this is the distribution that is defined by the normal probability density curve. Okay, so the normal probability density curve are recognized by their typical bell shape, and this is the typical bell shape. So when we plot our biological data on a curve on the graph, we're going to have this particular curve. So you can have an example of age distribution of pediatric population with overlying normal probability density curve. Now, there are so many things we can study about this particular unique curve in statistics. Of course, it should be viewed as a histogram. Okay, you view it as a histogram having a point of rise, a peak, before it eventually falls before it eventually falls. Now, at the top of it, you can see the top figure, this particular one, the dark bar of this histogram actually correspond to less than 9 age, less than 9, that's 9 months, okay? And that forms about 40% of our distribution from this particular graph. While for the bottom figure, the shape under the curve, it also corresponds, this shape under the curve, it actually corresponds to the same less than 9 months age, okay, which is approximately 40% curve, okay. So this is the histogram, and this is our probability density curve that we are making from our histogram, okay. Now, there are two important parameters when we deal with probability curve, and that is our mean and our standard deviation. For the normal probability curve, it has two parameters, the mean and the standard deviation. We call it the expected mean, okay? The expected mean is the expected average of the entire population. And of course, the mu, or sorry, the sigma is the standard deviation for the entire population. When we do population study in statistics, we look at the mean of that population and the standard deviation, and they are all represented this way. Okay, so the mean controls location for our normal probability density curve. It determines location, while our standard deviation talks about the spread. Okay, the higher the standard deviation, the flatter our curve is going to be, while the higher the mean, the skewed the curve is going to be. Good. So it's also important to understand that our mean and standard deviation is what form this our density curve. Okay, from this point is our mean. To the left and to the right is our standard deviation. Okay, so we have the mean here, and then we have our standard deviation. The standard deviation is established at the point of inflection, the point at which we see a sharp bend of the curve. That is our point of inflection of our curve. Okay, and it is one standard deviation away from the mean. If you have the mean at the middle here, from this mean to this point of inflection is one standard deviation to the left and also to the right. Good. So we can practice, it's important you practice how to draw this particular curve because it is very central to statistical inference. You can also feel the curve at the point of this inflection, okay, where the slope actually changes. And of course, it's important you know how to correctly label the horizontal axis and the vertical axis, okay. Now, there are two types of mean and standard deviation generally in statistics. When we deal with the entire population of interest, the mean and the standard deviation of that population are both referred to as parameters. The mean and the standard deviation of an entire population are both referred to as parameter. But if we are to take a sample from the population, and from the sample we obtain from the population, we obtain the mean of the observation within the sample and also a standard deviation. Now we refer to those two values as statistics. So you can appreciate there's a difference between parameters and statistics. Even though they are related, they are not the same thing. We talk of parameter when we are looking at the number summary or the spread derivation we obtain from the population, while we describe the number summary for a sample and the spread of it as indicated by standard deviation as statistics. Now we're going to talk about the 68, 95, 99 rule for normal distribution. What does it actually mean? Now, usually when you see the curve that we have drawn earlier on, you will realize that that curve has an area under it. We can describe the area under this curve based on mathematical formula. Okay, 68% of the area under that curve actually falls between plus and minus one standard deviation of our mean. While 95% of our area under curve, the A you see here means area under curve, it falls within plus and minus two standard deviation of our mean. And of course, the 99.7% of the area under our curve lies within plus and minus three standard deviation of our mean. Now, what are we saying about this? What does it actually mean? Now, when you have the mean of our curve at the middle, to the left, we have one standard deviation. To the right is one standard deviation. So you can appreciate that our 68% observation falls between one standard deviation plus and minus, plus and minus. So that is what this first statement means. Okay, our 68% central value falls between plus one standard deviation and minus one standard deviation from our mean. Same thing with our 95% central observation. From the mean here to this point, it is two standard deviation, and to the right hand side is also two standard deviation. That is exactly what we have up here. Same applies to the 99.7% of our observation under this normal distribution curve. It falls between plus three standard deviation and minus three standard deviation. Now, let's look at an example of our 68, 95, 99.9% rule. Now, we have an example here. Westler adult intelligence score is presumed to be normally distributed. Now, it's important to understand that before you can apply the normal probability density curve to explain any data set, it must come with an assumption that the data set is normally distributed. It is a central assumption before our normal distribution curve can actually be used to explain any data set. So let's say the Westler adult intelligence score is normally distributed. Now we have a mean already indicated as 100 and a standard deviation of 15. Okay, so if we are to look at the implication of this as it affects our 68, 95, 99.7 rule, it simply means that 68% of our scores are within what? The mean and plus or minus one standard deviation. So it simply means if you have our mean written here, plus or minus 15, which is the standard deviation, it simply means 68% of the total score of this Wesley Adult Intelligence score is between 85 to 15 to 115 in terms of score. And again, we can also apply this to our 95% of the scores, which it will be between two standard deviation plus or minus our mean. So if you punch this into our uh, our range, we're going to have 100 plus or minus two standard deviation, which simply means the value of score we're interested here will be 70 to 130%, 130. And same thing applies to the 99.7% of the score. Now, what are we saying here is that when you have a data set that is normally distributed, if you are given the mean of the data set and the standard deviation of the data set, you can construct the curve of that particular distribution, of that particular data set. So we are saying that our normal distribution is completely defined by the mean and the standard deviation. Simply means if you know the mean of a class, let's say you have a particular class and that class maybe fifth year students, sixth year student, fourth year student, and you are giving the mean age of the member of that class, and you're also giving the standard deviation, you can determine certain things about that particular class. Okay, you can even construct the curve of that particular class because the normal distribution is completely defined by the mean and the standard deviation. So we can see the example here, and this is our construction at the end of the day. So we put our mean at the middle, and because we have standard deviation is 15, so to the right of the mean, if you add 15 to 100, you are going to get 115. If you subtract 15 from 100, you get 85. So you can see that to the left and to the right of our mean is 68% central value. Okay? The normal curve is symmetrical. The curve moves up, peaks, and then goes down. Because the curve is symmetrical, the total area under the curve is exactly 1, or otherwise you can refer to it as 100%. So you have the curve going up and coming down. The total area under it is described as 1. Okay, and of course the probability is 1, and you can also express it in form of percentage. So with this we can easily determine the area under the curve. A shaded portion of the curve can be determined using our 68, 95, and 99.7% rule. Now let's have an example. Let's say we have a, a, a data set about the height of male, and we have been told that the mean age is 70 with a standard deviation of 2.8. Okay, now if we plot this on the graph, this should be 68. Please let's take note of this. This should be 68%. So if we plot this on our graph, we're going to have if 60, the central 68 is here, it simply means the two other 10 should be 16 to the right and 16% even to the left. So the mean height, like I said, the mean is 70 and standard deviation is 2.8. And our 68% will lie between 67.2, this 67.2 and 72.8. Why? It now means that if we remove 68 from 100, we're going to have 32 left. So dividing 32 is what gave us 16% to the right and 16% even to the left. Okay, and that implies that the normal curve is symmetrical, that is evenly divided. If you divide it along the line of the mean, you're going to have 50% to the right and 50% to the left. Thank you very much. This is the module we're going to take in this class, normal probability distribution.